Okay, welcome to lesson 311. This is called local linear approximation, and here's sort of the overview of what's going on. So let's say we've got some function f of x, whose graph you can see here. But let's say that maybe it's a function that we don't know the equation of, or even if we do, that it's not one that's necessarily easy to evaluate for all values of x. But maybe I do know, say, the value of f when x is 3. So I know this specific point here. But maybe I have a need to find the value of f of 3.2. So again, that's right next to that. So I need to know the value of f at that point right there. Well, again, if this is a function that's maybe not easy to calculate, or maybe I don't have enough information to calculate it, what can we do? Well, you've been learning in this class about the derivative and about tangent lines in particular. And the idea is, if I were to zoom in to that point of tangency, remember the idea is that as I get closer and closer to this graph, the tangent line and the function itself actually get fairly close to each other. And so the idea is we can use the tangent line, which is just a basic linear function, we can use that tangent line to approximate the function value at the same value of x. So that's the idea behind what we're doing. So again, we're using the equation of the tangent line to find an approximation for the value of the function at a value of x close to this point of tangency. Okay, but now remember, to find the equation of a tangent line, or any line for that matter, there are two things that you need to know. You need to know the slope of the line, so that's your m, and you need to know a point on the line, and that would be your x1, y1. But remember, in this case, the line whose equation we're trying to find is a tangent line. So specifically, the slope in this case is actually going to be f prime at a. And the point is going to be a, comma, f of a. So really, that turns this equation into y minus f of a equals f prime of a times the quantity x minus a. And then because we're actually going to use the equation of this linear function as an actual function to solve for y, let's actually move this minus f of a to the other side. So I'm just going to end up rewriting this as y equals f of a, so I just added the f of a to the other side, plus f prime of a times x minus a. So this is what we're going to end up using as our linear approximation. Okay, so let's take a look at a few examples. Now, I've told you before that we have in AP Calculus this rule of fours, sorry. And so remember, the idea of rule of 4 is that you're hopefully going to understand a lot of the different calculus concepts from various angles, sometimes from a table, sometimes from a graph, sometimes analytically, sometimes verbally. And so you're going to see several of those different approaches throughout these examples. Okay, let's look at the first one. Okay, so selected values of the derivative of the function g are given in the table. It is known that g of 2 equals 7. What is the approximation of g of 2.3 found using the line tangent to the graph of g at x equals 2? Okay, so that was a lot of information, a lot of words, but again, notice what they're trying to talk about here. We have some function g. We don't know what that equation is for that function, but we do know that g of 2 is 7. And we know that we're trying to approximate, and that's really going to be a key word here for when this shows up in future kinds of questions or on the AP exam or on your final. Approximation is a real key word here. So we're trying to find an approximation for g of 2.3 using the tangent line to the graph of g at x equals 2. Okay, so in other words, this is that x equals a that we were just talking about in this formula. Okay, so remember, we need to know what is the slope. That's going to be f prime of a. And we need to know the point. That's a comma f of a. Well, in this problem, we're not dealing with f, we're dealing with g. So the slope is going to be g prime of a, but again, that's 2. So g prime of 2. And our point is going to have to be 2 comma g of 2. Well, I can see from the table that g prime of 2 is 1.8. And I can see from the information that they gave us that g of 2 is 7. So that turns this into 2, 7. So now I have all the information that I need to write the equation of my tangent line. So remember, that's going to be y equals f of a plus f prime of a times x minus a. So that now becomes y equals, now f of a, again that's g of 2 in this case, so that's going to be 7 plus our slope, which is 1.8, times x minus 2. So this right here is our tangent line. Okay, and so now, if I'm trying to approximate g of 2.3, so that's going to be approximately equal to y of 2.3, meaning I can approximate g of 2.3 by substituting 2.3 in for x in this tangent line equation. So that now becomes 7 plus 1.8 times 2.3 minus 2. So that's 7 plus 1.8 times, no, 2.3 minus 2 is going to be 0.3. And I get 7 plus, now 0.3 times 1.8 is going to turn out to be 0.54. And 7 plus 0.54 is 7.54. And that is our approximation for g of 2.3. Okay, and again, notice we didn't know anything about the function g, but we did know that the derivative of g at 2 is 1.8, and so I was able to use the equation of its tangent line at 2 to find an approximation for g of 2.3. Okay, let's look at another one. Okay, so let h be a differentiable function such that h of 4 equals negative 8 and h prime of 4 equals negative 0.4. What is the approximation for h of 3.8 using the line tangent to the graph of h at x equals 4? Okay, now this is a little bit different from the previous example. In the previous example, you had an entire table of values. So again, in that rule of 4, remember one of the ways that you're supposed to understand a concept is from a table representation, and that's what we had in example 1. Here, it's actually a little bit more in words. So let h be a differentiable function such that h of 4 equals negative 8. So right there, h of 4 equals negative 8. Remember that that's giving us the coordinates, or the point, of our tangent line. So the point is at 4, negative 8. It says, and h prime of 4 is negative 0.4. Well, h prime of 4, that's our slope. Oops. So h prime of 4, and we know that that's negative 0.4. So I now have all the information that I need to write the equation for my tangent line. So once again, that's going to be y equals, so it's my f of a, or in this case, h of 4. So I have negative 8 plus my slope, so actually that's a negative, so negative 0.4 times x minus 4, which is our a. So this is our tangent line equation. And so now if I'm trying to approximate h of 3.8, that's going to be approximately equal to y of 3.8. So that's going to be negative 8 minus 0.4 times 3.8 minus 4. All right, so now I'm going to get 3.8 minus 4. That's going to be a negative 0.2. I have negative 8, so negative 0.4 times negative 0.2 is going to be a positive 0.08. And negative 8 plus 0.08 is going to give me negative 7.92. So that is our approximation for h of 3.8 using this particular tangent line. All right, looking at another one. So let f be a function such that at each point xy on the graph of f, the slope is given by dy dx equals 2x minus y squared. The graph of f passes through the point 3, 2. What is the approximation for f of 2.9 using the local linear approximation at x equals 3? So again, this is a little bit different from the previous examples. In the first example, remember you were given a table. In the second example, you were just given a bunch of information in words. And in this one, it's in words, but you're also finally dealing with an actual equation. So this is more of the analytical approach. Okay, so once again, we're still being asked to approximate at f of 2.9, and again, we're still using that local linear approximation, and so the first thing we need to understand is that that means we need to find the slope of the tangent line, so the derivative at 3, and we need to know the ordered pair when x is 3. Well, we know that the ordered pair, we already know that the point is 3, 2, that's what they gave us, and we know that the slope, m, is going to be dy dx evaluated at 3, 2. But they gave us the equation this time. So that's going to be 3 times x, so that's 3 times 3. Oh, I'm sorry, not 3, 2. So 2 times x, so 2 times 3, minus our y, and that's our 2, squared. So 2 times 3 is 6. 2 squared is 4. I got 6 minus 4, and that gives me 2. Okay, let me go ahead and move all of this down so I've got a little bit of space to work. Okay, so I now know my slope and I know my point, so now I can write the equation of the tangent line. So this is going to be y equals 2 plus, our slope was 2, times x minus 3. And now we can finally approximate f of 2.9. So that's going to be approximately y of 2.9, which is 2 plus 2 times 2.9 minus 3. That's 2 plus 2 times a negative 0.1, which is 2 minus 0.2, which gives us 1.8. This time, however, there's a part B to the question, and even the previous questions could have had the same question pop up, but you would have had to have been given the information in other ways possibly. So it is known that f is concave up on the interval from 2 to 4. Is the approximation for f of 2.9, meaning the approximation we just found, is it an overestimate or an underestimate? Explain. Okay, so again, they're asking, this 1.8 that we just found, we know that that's an approximation, so we know it's not exact. Is this approximation too high? Is it an overestimate? Or is it too low, an underestimate? And they mentioned this thing about f being concave up on this interval from 2 to 4. Now, what's the significance of that? So first of all, notice on the interval 2 to 4 that that does include our a and the value at which we were using our approximation. Okay, so on that interval, our function is concave up. Now let's think about that visually for just a moment. If my function is concave up, then remember what that means about the way that the function relates to its tangent lines. It means that all of the tangent lines lie below the graph. Hopefully you recall that from when I first introduced concavity to you. Now remember though, our approximation was actually on one of these tangent lines. So if my approximation is on the tangent line, and my graph is always above the tangent line, then that means my approximation is clearly too low because it is literally below the function. So because this function was concave up, they told us that, then that means our approximation must be underestimate because the function lies above its tangent lines, or you could say that the tangent line lies below the function. Okay, so let's go ahead and write that out. So the approximation is an underestimate. It's too low because the tangent line lies below the function. So that's another connection that we need to understand regarding concavity. So remember, because this function is concave up, the tangent line lies below. Because our approximation lies on the tangent line, then that means that the y value is below the actual y value. And again, if this function were concave down, then of course all of its tangent lines actually would lie above. So if I had an approximation on this tangent line, clearly that's actually higher than the actual value. So if we know that our function is concave down, then that means we know that our approximation is actually now an overestimate in this situation. Okay, so now let's kind of wrap this up with one last example. So given the function f of x equals 3e to the x minus 2, find the approximation for f of 2.1 using the local linear approximation at x equals 2. And then is this approximation an overestimate or an underestimate? Explain. Okay, so again, we're still being asked to approximate using linear approximation, so I still need to know the same two things. I need to know what is my slope and what is my point. Well, at x equals 2, let me change colors here. So our point, we need to know 2 comma f of 2. But to find f of 2, we actually have the equation of the function this time. So f of 2 is going to be 3 times e to the 2 minus 2. Well, that's 3e to the 0, which is 3 times 1, which is just 3. So our point is actually at 2 comma 3. Now for the slope, remember for the slope, we need to know f prime of 2. Well, in order to find f prime of 2, I actually need to find f prime of x first. So we've got this exponential function. So remember, if f of x is 3e to the x minus 2, then f prime of x is going to be, so this is just a constant times a function, so it's going to be the constant times the derivative of this function. Now this is not just e to the x, it's e to the u, so the derivative of e to the u is e to the u times the derivative of u. So our derivative actually turns out to be exactly the same thing. So that means f prime of 2 is just going to be what we just did on f of 2. So this is going to be 3e to the 0, which is just 3. Okay, so now our equation for our tangent line, we have y equals, so again it's 3 plus 3 times x minus 2. And now we can approximate f of 2.1 by substituting in. So I've got 3 plus 3 times 2.1 minus 2. That's going to be 3 plus 3 times 0.1. That's 3 times 0.3, and we get 3.3. Okay, now finally it says, is this approximation an overestimate or an underestimate? We still need to determine that the same way, which is looking at concavity. So remember, we use, if we're looking at the equations, we determine concavity from the second derivative. Well, we already know that the first derivative is 3e to the x minus 2. So that means the second derivative is the derivative of that, which is 3 times e to the u times the derivative of u, which again gives us the exact same function. So remember, we need to know what is the concavity at these values or on that interval. So let's just use f double prime of 2, which is our a value. So if I look at f double prime of 2, that's going to be 3 times e to the 2 minus 2, which again is going to be 3e to the 0, which is 3. But more importantly, that is positive. And remember, if our second derivative is positive, then that means our function must be concave up. Okay, so again, I evaluated the second derivative at my a value. And I saw that the second derivative was positive, and that means that our graph must be concave up, And because the function is concave up, then that means we know that our tangent line lies below the curve. So therefore, the approximation is an underestimate. And again, that's because the tangent line must lie below the function. In this case, that's f of x. And that is local linear approximation. So again, it's all about finding the equation of that linear tangent of the tangent line, using that equation of that tangent line to find the value or an approximation for the function value. If we're trying to figure out whether this is an overestimate or an underestimate, we need to look at the concavity of that function on that interval. Okay, good luck.